So now we have looked at Flash ADC in some detail, and we know that, I already mentioned that we don't use Flash ADCs for resolution greater than 5-6 bits, right? But there are a couple of tricks that you can use to improve the resolution by a couple of bits. Let's look at one of them. So let us say I have Flash ADC. We know that we are going to have an array of comparators, each comparing the input with different reference voltage. So let us say here I have a reference voltage VRK plus 1. Let's say this is V reference K, and here it will be K minus 1, so on. Okay. Now let us say I want to increase the resolution by 1 bit. What can you say about the number of reference voltages I will need? If I increase the resolution by 1 bit, what can you say about the number of comparators I will require? For an n-bit comparator, how many comparators I need? So how many reference levels I will need here? Same, right? If I increase the resolution by 1 bit, what happens? It kind of doubles. So along with these reference levels, I also need to have additional reference voltages. And where might the additional reference voltages be? Here. Huh? No. You will have to have in between them. Is that fine? So between every 2 pairs of reference voltages, I will have to go and introduce one more reference level here. So if I consider only this guy, what is this voltage? Average of the 2, right? So this will be, let's say, VRK. Okay. So now let's say I will draw a single-ended case to start with. So let's say this is the kth comparator. I have, so let's say I have the pre-amplifier. The single-ended case I will consider. So this is from V in. This is, let's say, the kth reference. I will call it VRK. This is then given to the latch, and the latch will make the decision. If this gain is A, what is this voltage? Okay. Now I'll also have the kth branch. So let's say here I draw this is, let's say, the K plus 1th branch. So it's comparing with K plus 1. So this is what we have in a normal flash. So now let us say I have to increase the resolution by 1 bit. In between these two guys, I have to go and introduce one more branch here. And this is A. The reference voltage here should be the average of the 2. And we have the latch. So what is this voltage? Minus that, right? So let's say, but let's say if I do this, I am simply increasing the number of resources I need in my circuit. Let's say I don't want to do it. I want to do something better. Okay, this is basically a brute force way. This, we are not doing anything, right? So now if you see, I need the extra digital output. So I need this latch for sure. That is something I cannot get away with, because I need some latch to make decision. But let's see if we can get away without using the preamplifier, right? So let's say I don't want to use the preamplifier here. Now remember that the goal of the preamplifier was to generate a voltage which is this. Now look at the circuit and tell me, is there some other way in which I can generate this voltage? If you basically take the average of these two, that will give the required voltage, right? And what is the simplest way in which I can take the average? I can basically connect two resistors. Okay. If I do that, I will get the average of the two, and we can basically get away without using one additional preamplifier. Between each branch, I am removing one preamplifier, so the number of preamplifiers required reduces by a factor of 2. So this technique is called interpolation, and in particular this is referred to as 2x interpolation for obvious reasons. So let us say now I want to have a 4x interpolation. What do I do? Right, because if I want of 4x, I will go and have to introduce one more reference level like this, and that I can do it by basically splitting this guy into two. I'll go and put one more latch here. Similarly, this I'll put two resistors. Now this is a 4x interpolation, right? And actually, if you look at a differential implementation, the 2x interpolation becomes much more easier. So let's actually look at that. So let me draw a differential case. So this is a differential preamp. Gain is A. So I'll just say that the differential input we have is some Vin minus some VRK, right? So what is the differential output? A into that. So what can you say about the positive output alone? No, it's not grounded, right? It's a differential. It's a fully differential amplifier. See, I know that difference. If the input difference is so much, the output difference is gain times that. What can you say about just the single-ended one? It's a fully differential. It's a fully differential case. That is, if I look at the difference is so much. In a fully differential case, what can you say about the two voltages? Basically this will be, these two will be negatives of each other, right? So what can you say about the positive one? Yeah, A into A by 2. Again, you'll have a common mode. I'm ignoring the common mode, and the other one is minus this. Fine. And remember, this goes to a latch. So I'll have same for the k plus 1 branch. So let's say k plus 1. This. Yeah. So in principle, I need one more branch in between. Let us say this is the latch I want. And ideally, if I were to have one more preamplifier and put it, what would be the output of the preamplifier differentially? What is the reference voltage I want to compare the input with? So basically, I want to have Vin. This is the voltage I want, right? So now look at the circuit and tell me what is the simplest thing I can do so that if I take different, basically what I want is, I want to take the difference between two voltages, and that difference must be this. No, look at the circuit. Here you can't put resistors. So what is the simplest thing you can do? I want to take the difference between two voltages, and that should give me this. Is there two voltages in the circuit? One positive and one negative of this. Is that okay? Yeah, then its sign will be reversed, but that's okay. Right? So here if I say take the difference of these two guys, A V in by 2 and minus of minus A V in by 2, we get A V in, and similarly you will get the required reference also. So what you have to do is this, connect this guy to here, this guy to here, and you get a free extra information. So you get a simple 2x interpolation here. Now this is the nice thing about this interpolation is that we have basically eliminated the required, the number of preamplifiers in the circuit, right? So if although I'm increasing the resolution by 1 bit, I'm not doubling the number of preamplifiers. So if I'm not doubling the number of preamplifiers, that is good, because here in a flash ADC, you know that the inputs are all, let me use a different color maybe. All the preamplifiers take the same input, and this input is being driven by some buffer before. If I am reducing the number of preamplifiers, the input capacitance that the effective preamplifier, the preamplifiers present to the previous stage, which is the buffer, is reduced, which is nice. But what do you think could be the downsides of this technique? Sorry? There will always be? This is what you want, right?
But in this case, average will be always there.
No, I mean, this is basically voltage, right? It is, I understand. You want the average of these two voltages, and that needs to be compared. That's what you want.
If it is already getting compared.
But this comparison is what you wanted, right?
What I am saying is 1 0 0 0 is voltage I want, means bits I want.
Okay.
But this middle one is giving some other voltage by taking average of this.
No, but that's the additional information you want, right? See, you are basically already made decision with respect to these two. You want to make a decision with respect to this level, and that is what is being done. Let us say this could be 1, this could be 0, but you don't know what is the output of this comparison. Okay, think about it. Huh? Yeah, that is actually one thing. So resistors need not, but it turns out resistors can be matched with decent accuracy. Okay, I mean, one simple thing is, see, here it requires that I have to use a preamplifier. I mean, it can so happen that in my case, for my comparator, I don't even require a preamplifier, right? I can just tap the latch directly.
Yeah.
But for this trick to work, I definitely have to have a preamplifier, right? And secondly, as he was pointing out, one of the issues is this, right? So this entire premise is based on the assumption that if I take the average of these two, I get the required voltage. But here, if you have the two amplifiers, their gains need not be exactly equal. The moment you have mismatch in these two gains, you are completely screwed, right? So because of all these reasons, this was done in the olden times, but matching A is very difficult. Yeah, actually it turns out in CMOS processes, matching resistors and capacitors can be done better than matching transistors.
Yeah.
So the gain matching will be much more difficult. Right? So because of all this is not done commonly now. But what is done in the recent past is a different kind of interpolation. We'll look at that. So that is a little bit more common. So let us say again I take the same case. I have a reference VR k plus 1, ARK. We want to get an additional comparison with respect to this VRK plus VRK plus 1 by 2. Right? So we'll again draw two things. Now let's say there is no preamplifier. I am directly using the latch. Can have a preamplifier also, but doesn't matter. And remember, this is the, let's say, our strong arm latch. To make sure that the output of the latch is held for one whole clock period, what did we have to do at the output? In a strong arm latch, the output was reset in one phase and it was available only in one phase, right? But if you want the output to be available for one whole clock period, what did we add at the output? We added an SR latch, right? So basically that was there to simply hold the digital data for one whole clock period. This is how any latch will have. This latch is to make the comparison, this is to hold the output for one whole clock period, right? Sorry. So here let us say we are comparing with PRK. So let us say this guy is some QK, this is QK bar. So we have the k plus 1 branch. So let's say this is k plus 1, k plus 1. We see, yeah, to keep the information held for one whole clock period. That's all. Only then the succeeding digital logic can process the data. Great. So now let us say my input is somewhere here. What can you say about the output of kth comparator? This is the kth reference voltage. The input is somewhere here. 0. And what should be the output of this? 0. So if input is lying somewhere here, it's easy, right? Similarly, if the input is lying above the k plus 1th reference, what can you say about the outputs of these two? 1. So which means if these two are 1, this is also 1. That is at least clear, right? So the issue comes when the input is lying somewhere in this range. Okay, so now let us say I consider the input to be lying somewhere here. What will be the output of the kth comparator? That will be 1. What will be the output of the k plus 1th comparator? 0. So let me also mark that. So this guy is 1, this is 0. Fine. And if the input is lying here, what should be the output of this comparison? 0. Our goal is to deduce that this result is 0 based on only the results of k and k plus 1 comparator, right? So now it is true that the output of kth comparator is 1, k plus 1th comparator is 0. But do you think both the comparators will regenerate and give the output at the same time? Or do you think one comparator will take longer time to regenerate? To give the output. The input is lying here, right? The kth comparator is comparing the input with this reference voltage. The k plus 1th is comparing with this voltage. So which of the comparators do you think might take longer time? Why? Yeah, remember that if the input difference the comparator is sensing is small, it is going to take longer time. Yeah. So here the difference is this much. For the k plus 1th, it is so much. So which will finish faster? Upper one will finish faster, right? So if I basically were to sketch the outputs, so remember that in one phase both the outputs are at VDD in the strong arm latch, and let us say this is when the comparison starts. Okay. Now the top one finishes quickly, so let's say it does this, and this is qk plus 1. The bottom one will take longer time, so let's say it does this. So this is qk. Fine. Now as I keep increasing this input voltage, what can you say about the delays of the two comparators? No. If I let's say increase the input voltage, what will happen to the delays? Delay for the bottom comparator, what will happen if I increase the voltage? That will decrease. For the top one, it will increase. So under this will happen, and when will the delays of the two comparators be equal? If the input is lying exactly at this point, that is when the deltas seen by the two comparators are same, and only then the two comparators will have the same delay. And when you cross this guy, situation reverses. Voltage is at the reference, what is the output? That, see, if you are saying for a comparator, this is basically you are saying if you have a comparator, differential input is 0, what is the output? Right? I mean, that is not defined, right? Not this is the, so what will happen is at that instant, whatever noise is there, that will make the input. But at least this point clear. So as long as the input is lying in this range, the top comparator will regenerate faster than the bottom one, right? So let me write that. So here in this case, qk plus 1 bar goes to 1 much before qk, right? So qk plus 1 bar goes to 1 before qk. And in this, when this happens, what do you want the output of the additional comparison level to be? You want 0, right? Because if the input is in this range, you want the comparison to be 0, and as long as the input is in this range, the top comparator will respond quicker than the bottom comparator. So in this case, I want, let's say, q out as the additional bit to be 0. I mean, I can also look at the complements. I can also say that qk plus 1 goes to 0 before qk bar. Both are same, right? So let me actually copy paste this. So now let's say yeah, now let's say my input has gone to this level, this side. Let's repeat the same. So what can we say about the output of the kth comparator? Input is lying here. Will the output of the comparator be 1 or 0? 1. For the k plus 1 comparator, the output is 0. The outputs of these two comparators don't change, but the output of this comparison, what will it be? It will now be 1. Right? Because input is here, this is the reference voltage, the output should be 1. And if the input is lying in this range, which comparator will respond faster? The bottom one, because delta is much larger for the bottom one. So the situation simply reverses now. So this will respond slower, the top one. This is Qk plus 1 bar. Sorry. Whereas the bottom one will now respond quicker. Right? So this will basically mean that Qk is becoming 1 much before Qk plus 1 bar, or the complement Qk bar goes to 0 fine, sorry, 0. Basically here Qk goes to 1 much before Qk plus 1 bar, or the other way to look at is Qk bar goes to 0 before Qk plus 1. And when this happens, what do you want the output of this comparison to be? You want this to be 1. Right? So these are the two pieces of information we have. So now it is actually much simpler, right? So we have two pieces of information. We see that if I can take any two, let us say I take this guy. Now I just have to compare Qk plus 1 and Qk bar. I find which of them goes to 0 before, and based on that I make the decision, additional bit. That's all. Right? You see, because you see that if the input is lying in this range, the top comparator is making decision faster. If the input is lying in this range, the bottom comparator is making decision faster. I just need to check which of them is responding quicker. That's all. Right? So, and that translates to this, right? I can either look at Qk plus 1, that is Qk plus 1 and Qk bar, or these two. I'm just looking at the first option. That's all. So now tell me, right? I just need to come up with a way to detect which of these two is going to 0 before. Now it's mostly a digital problem, right? Because you just want to see which of the two signals goes to a logic 0 quicker. So you guys all have taken digital electronics course. The last I took course was 10-12 years back, so you guys should be fresh. Help me. What is the simplest circuit that you know that can do this? And no, right? I mean, if I have NAND, remember that both of them eventually go to 0. Both signals eventually go to 0. I just need to detect which is going faster. I mean, I'll tell none of the logic gates as such will work directly. Okay, let's see. Let's write down what the information we have, right? I am looking at, let's say, Qk plus 1 or Qk bar, Qk plus 1. Based on that, I want to find Q out and Q out bar, let's say, right? First thing says if Qk plus 1 goes to 0 before Qk bar, this is 0, right? So I'll write like this. So Qk plus 1 goes to 0, whereas Qk bar goes to 0 after some delay. my own notation I'm using. In this case, it should be 1, this is 0. And the other phase, it is opposite. Fine. So I have, let us say, qk bar, qk plus 1, q bar. So let us say, where can we? Let's say we are initially, let us say q bar is 0. Okay. And let us say we are in this situation where qk bar is becoming 0 first. And notice that when the comparator starts, both the outputs initially start at logic 1, and then one of them goes to 1, one of them goes to 0. Right? So initially, both these guys start at 1. Now, in the situation I have considered, qk bar goes to 0 quicker. So let us say this goes to 0 faster. In that case, I want this to go to 1. Right? When qk bar goes to 0 faster, I want q to be 1. So this is the scenario I have. I have qk bar to be 0, q bar to be 0. I want to use these two to make this to be 1. What is the simplest logic, you know? When both inputs are 0, output should be 1. Not NAND. Only when both inputs are 0, it should be 1. NOR? Not XOR, right? It should be NOR. I mean, remember OR gate? I mean, NOR is complement of OR, right? So for OR, if 0 is only if 0 0 is there, the output for OR gate is 0. So for an OR gate, this becomes 1. Okay. So this is what we have, and let us say qk plus 1 becomes 0 after a long time. So this, right? So now later qk plus 1 becomes 0. I want this to be still at 0. So I have 0 and 1, and the output should be 0. I can again use an OR gate here. Right? For NOR gate, if one of the inputs is 1, the output is 0. So this will remain at 0. So you can use this actually. What is this? It's an SR latch, right? It's an SR latch. NOR based SR latch. Okay. So now you see the simplest thing you can do is, I'll take our existing Flash ADC. I'll first remove all these. Yeah, same SR latch is enough. You can use NAND or NOR, anything. You just need to, if you are using NOR, you just need to complement. I mean, if you take inversion, it's all right. Otherwise, so all I have to do is take one more SR latch here, right? And the inputs I have to give them are qk bar and qk plus 1. That's all. I'll give them the correct thing. Sorry, what are the inputs? Qk bar, right? Qk bar and qk plus 1. So that's all. You see that anyways, after every strong arm latch, you need an SR latch. Now I'm just putting one additional SR latch. I'm getting an extra bit of information for free. So in between every two branches, you go and put an SR latch, taking the positive input of the upper side and the complemented input of the lower side, and that will directly give you the information. Okay. So here if you see, we are doing interpolation, but we are not actually using the information in voltage, right? In the earlier case, we are doing some interpolation in voltages, but here what information is available in which format? Yeah, digital, but we are basically checking which signal is coming before in time than other signal. So information is basically available in time. Okay, so we are exploiting the time delay in the two signals. So the information is actually available in time. Okay, so this is called as time-based interpolation. So here we took QK bar and QK plus 1, and then we used a NOR based SR latch. If I were to, I can also as well use these two, right? QK and QK plus 1 bar, and check which of them goes to 1. And for that, what kind of SR latch I will use? I will use a NAND based SR latch. Just think about it. I mean, because here the inputs are going to 0, I am checking which of them is going to 0 earlier. I am using NOR. If I took the other outputs, I have to check which of them is going to 1 earlier. In that case, I have to use a NAND. Can you say that? And this is something that is done commonly. And I can show you the first thing that did this. Yeah. So this is one of the earlier papers that came up with this technique. Right? And this was from Yanxiang Xu from MediaTek. So here what they have done is to realize a 6-bit using a 5-bit flash, and then one extra bit you get from this timing thingy, right? So you can just show the thing. Is it visible? Yeah. So yeah, here we have the two comparators, and as we discussed, you give it to an SR latch and then get an additional bit of information. So here VOS is basically the reference voltage, and you are getting the additional comparison with the average of the two by simply using an SR latch. Okay. And even if you look at the comparator they have used, so this is the comparator. If you see this part alone, what does it remind you of? You have a differential pair. No, you have a differential pair and then you have a cross-coupled inverter. This is your strong arm latch. The only difference is basically, if you see, they have an array of differential pair at the bottom and then the tail transistor. And basically the equivalent circuit is actually shown here. And check here. Yeah, that's what I'm getting at. So this is the equivalent. The role of this is to act like a resistor here. And if you recollect, in the last class, I mentioned that you can intentionally introduce mismatch in the two branches to introduce an offset, and you can make the offset equal to one of your reference voltages in flash. Right? So same thing is being done here. You have a programmable array of transistors there below the tail transistor and below the differential pair to act like a resistor, and you introduce proper imbalance in these two halves so that you get an offset here, and the offset is close to the reference voltage you want. And that's why if you see the input is directly applied here, the comparison with the reference voltage is inherently done here. Okay. Great. So now let us say I want to extend this to 4x. This is basically a 2x interpolation, right? Let's say I want to get one more bit of information. That is, I want to interpolate by 4 times. Can you suggest me? You're saying what? And there is no one right answer, right? You can think, you might even come up with new solutions, right? Between? But I mean, remember, the SR latch is not having any information in time. The actual information is in the latch, which is making the regeneration. But I mean, okay, you guys are thinking in one of the right tracks. It looks like I can do one more level of interpolation, but for that, this should not be an SR latch. It turns out in sometimes you can cascade multiple latches and then finally have the SR latch. Just like how you cascade amplifiers to increase the gain, you can as well cascade latches to get a faster regeneration. So let us say you kind of have a cascade of latches. Yeah, you have to do it before that. That's what. There are some issues in this, but this also can be done. You can, just like how we saw, if this was a pre-amplifier, you can do it, right? So something like that. So you can do one more latch here, and then between these two you put one SR. Here you will have one more SR. You can do that also. Actually, this is also being done. I mean, this has also been done. Yeah, so this is 2015. And by the way, this time domain interpolation was first introduced in 2012-2013 when I was still doing my BTech. Right, around 10-11 years back. Okay. And here they have done this cascaded latch interpolation. So again, I'll only show it. Yeah. So as I mentioned, let us say you have a cascade of two latches in the k and k plus 1 branch. You first have an interpolated latch and then have the SR latches here. So this way you can get a 4x interpolation. That is, along with the number of bits, let's say you get n bits from the flash. From here you can get 2 extra bits. So the resolution becomes n plus 2. But there is a much cleaner way to introduce, to get a better interpolation factor. So actually, if you think about it, let's say this is the k plus 1th reference, kth reference, this is the in-between one. I'll say it's VR k plus 0.5, okay, rotational abuse, but yeah. So if I actually sweep my input, so let us say the input is in this range, the delay of which comparator is longer, the down one is longer and the top one is faster, and when will the delays of the two comparators be equal? At the middle, right? So if essentially the input is exactly at this point, k plus 0.5, the delay of both top and bottom will be same. Now if I increase the input, the delay for which comparator will increase? For the top one it will increase, right? So for the top one the delay will look like this, right? And if I increase the input here, what can we say about the delay for the bottom comparator? This is, let us say, qk plus 1. For the kth comparator, if I increase the input, what happens to the delay? It will reduce, right? For the other one it will look something like this, right? And let us say this is your k and k plus 1. Now exactly if the voltage input is at this point, the delays of the two are same. So now what we have done is, our intention was to check if the input is greater than this or less than this. So we just checked if which of them is finishing earlier. Now let us say I want to get one more level of information. So I want to compare if the input is greater than this one. This is, let us say, k plus 0.25. Now you see that the kth one has a higher delay, and let us say that is by some delta t. Similarly, if I want to introduce one more level here, this is, let's say, k plus 0.75. In this case, the k plus 1th comparator has a larger delay by delta t. That right? Yeah. So what I have to do is, if we want to get information about if the input is greater than these two references, I should no longer check if the two comparators are finishing. I should no longer check if one of the comparators is finishing earlier than the other. I should also check if one of the comparators is finishing decision delta t before than the other. Here it was as though I am comparing if the delay was greater than 0 or less than 0. Now I no longer should compare just if the delay is greater than 0 or less than 0. I should also check if the delay is greater than delta t or greater than minus delta t. Okay. So this is the thing, but again this is what we have to do, and this logic can be done in a couple of ways. So one way is, I will show here. So this is again in 2015 in Asian Solid State Circuits conference by Professor Martin's group. So here they have done a 4x interpolation, right? And what they do is this. Yeah, this is the graph we also saw, right? So this is the middle reference. At this point, the delays of the two comparators are same. Now if I want to check if the input is greater than one of the reference to the left or to the right, I also have to look for this delta t difference. And the way they have done is like this. This middle latch is the same old. It just checks if the input is, if the two comparators are finishing at the same time or if one of them is finishing earlier than the other. Now in these two latches, we also have to check if one comparator is finishing delta t before than the other. So it is as though I have to introduce a timing offset in this latch, right? Now if you just recollect, for a comparator we saw that we can actually introduce imbalance in the two differential halves, so that the comparator doesn't compare if the input is greater than 0, it compares it with some offset. Now if you think about think about an SR latch, it also has two differential halves. Ideally, if they are exactly balanced, it will check if one of them is finishing earlier than the other. Now if I go and introduce intentional offset there, imbalance there it can check if the input is, one of the inputs is appearing delta t before than the other. Logic fine? So same thing is done here. So this is the SR latch, a NAND based SR latch. So they go and skew one of the sides. You can check out the details, so that this compares it with the offset of delta t. Okay, you can check for this paper for more details. Basically, you have to, the two NOR gates you have, or the NAND gates you have, they should not be. That's what it is. That's why it is much easier to say than to do. So there are other things to take care, but this can be doable. This is doable. It is not like people have done it, right? But it is not much. It is much easier to say things than to implement. True for anything, right? And here they have got a 6-bit flash, right? So and you can check. They give some more details here. Yeah. So in a 6-bit flash, you need 63 comparators, but these people use only 16 comparators, which is basically a 4-bit flash. And then by doing this 2x interpolation, they get the 2 extra bits. And if you also, do they have the comparators architecture? No. Yeah, here you can see the final output spectrum. So let's do some calculations here. Yeah, so here the input is this x-axis is in Fn by Fs. So this point is, let us say, roughly 0.23. Okay, so let me actually go up here. Fn by Fs is 0.23, so Fn is 0.23 times Fs. Okay, now where will the third harmonic lie? 3 times Fn, 16 Fs, but I am plotting the spectrum one-sided, 0 to 0.5 Fs. So where will it lie now? Again, please, everyone work out and tell me, because no, please take your time and tell me, because in the first quiz, except a couple of you, everyone got things wrong. So take your time and tell me. 0.69 Fs, but I am only plotting till 0 to 0.5. Where will this alias to?
0.3.
Huh? Remember that it's always aliases to kfs minus the frequency, right? So this is Fs minus 0.69 Fs, which is 0.31 Fs. And yeah, here is the third harmonic, around 0.3. Okay. Now you can also do this comparison in time in a different way. And remember, this is the logic. We just need to check if the time delay between the two outputs is greater than something or less than something. If I want to get more information, I have to, let's say I want to do this, then I have to compare for these times also. It turns out there is a whole class of circuits called time to digital converters. Or TDCs that can actually do this. It can take the delay between two digital signals, let us say, and digitize the time delay between the two. I will not go into details. If you are interested, you can refer to E698G lectures by Professor Chitra. So the nice thing about TDC is that it turns out to implement a TDC, you just need a bunch of digital blocks. Using some inverters and flip-flops can actually implement a good TDC. So I am not going to details. So what you can do is you can give these two guys QK, this is I think QK plus 1 bar or whatever, to a TDC and get more information. Okay, and this is also being done, and this has also been done and this is relatively recent. So it was in Journal of Solid State Circuits only a couple of years before. So here again they have done 8x time domain interpolation. Okay, so which means in addition to the number of bits you get from flash, how many extra bits they are getting? 3 bits. So you have to digitize the time with 3-bit resolution, and I think that's what they do. Yeah, they do a 3-bit time to digital conversion. Okay. So using that, basically they want total of 6-bit. So you can have a 3-bit flash and a 3-bit TDC. I'll not go into a lot of details, I'll just quickly show and we'll move on. Yeah, this is the basic thing. This is your normal flash ADC. You take the digital outputs of this and you also feed the signal so that you get a TDC. And again the logic is same, right? In between every 2 branch you go and put a TDC instead of putting a simple SR latch. You can think of an SR latch as a simple TDC. See, SR latch can be thought of as a TDC that just checks if the input difference greater than 0 or less than 0, that's all. It's like a single bit comparator. SR latch is a single bit TDC, it's like a single bit flash ADC, that's all. So in between every 2 branches you go and put this guy, and as usual you take the complement of the top side and the positive of the top side, positive of the bottom side. We saw QK plus 1 bar and QK, right? That's basically this. And then you can do this. And here also let's do some spectrum calculations so that we where is the spectrum? No. Yeah. So here also let's do some spectrum calculations so that you get comfortable. So here they are plotting a 4096 point FFT. So the number of points is 4096. So when you plot a one-sided spectrum, you start from 0 and end at which is 2048. So here the input is lying somewhere here, and let's say that's around 1900 or something, some rough number, right? See, of course, when you choose the input frequency, remember you choose it. How do you choose the input frequency in terms of the sampling frequency? It will be some m by n times fs. And how should m and n be? That should be co-prime. So here what is n? 96. So I cannot choose 1900 because that is not co-prime. So it could be some 1901 or something. But let's say for simple calculations let it be 1900. Okay. So let's do that. So n is 4096. My input lies on 1900 bin. So where will the third harmonic lie? So third harmonic will be 3 times m. 5700. But remember that I am only plotting from 0 to 2048. Okay. So you will have to look at, see, remember we always look at KFS minus the frequency. Here Fs corresponds to what value in the bin number? Yeah, 4096. So it's basically n minus the frequency, which is frequency bin, which is 5700. What happened? Okay, everything crashes. Let's see. Okay, this works. Okay. I think in tablet mode it's a problem. Yeah, 5700 minus 4096, right? I'll write here 4096 minus 5700. What is that roughly? I can think of it as, yeah, terribly sorry for this. Can it go down at least? Yeah. can work out 4096 minus 5700, roughly around 1600 or something, right? And that's where you get the third harmonic. I mean, that's why you should be really fluent in understanding. If you take an FFT where each frequency and each harmonic will lie, you should be very fluent in that. Okay. So yeah, so that's about interpolation. Now, in practice, there is one other thing that can be done. We can explain it, or let's see if it works. I'll explain. There is one other trick that was done in the olden times. I'll just say it for the sake of completeness. Okay, I'm not able to write. Okay. Okay, so what was done is this. So let us say this is the quantizer characteristics that you want to implement. In the positive side you have something, negative side you have the basic exact copy in the symmetrical way. So let us say I make an ADC which only compares with positive references. Okay. So this is the ADC. Where I have only having comparators which compare with positive references. Okay. Now to get information about this side, what can be done is this. Yeah, let's say you give the input, give it to a single bit comparator that says if the input is greater than 0 or less than 0. This is the differential input. Its job is to just tell if the differential input is greater than 0 or less than 0. Now if it is greater than 0, you have to search in this space. I can directly go and connect the input here. Okay. If it is less than 0, what can I do? Sorry? Yeah, basically what I will do is I will flip the connection here. Basically, if the input is greater than 0, I will feed the input directly. If the input is less than 0, I will give minus V in so that I can still use the ADC which compares with positive references. Okay. So the actual circuit will be this. You have a single bit comparator. Let us say its output is some D, and this is the ADC. We feed the input directly if the input is greater than 0. And we crisscross the inputs. Then D is 1, which means the input is greater than 0, I can use it directly. And if D is 0, which means the input is less than 0, I'll crisscross and feed the inputs. This is the same input, by the way. Okay. This technique was called folding. Again, this was introduced in one of the olden papers, but it is not commonly done now because, as we'll see later, you can do a much better version of this, and that's called pipeline ADCs. We'll come to that later. But again, the same principle of folding, just like how interpolation was initially started with voltage and people did in time, in principle you can also do this folding in time, and people have also done this. And you'll find that the general trend or the general motivation is to push most of the processing in time, simply because if I want to do things in time domain, I just need a bunch of digital blocks. For example, a simple SR latch, as you saw, was a time to digital converter which checks if the differential time is greater than 0 or less than 0. Right? Similarly, any processing in time just requires almost purely digital blocks. So the general push is to actually try to do more processing in time. Okay. And in fact, you will see, I mean, if you have time, we will see at the end of the class, end of the course, that there is one other kind of thought process wherein, see, we have a voltage signal, we want to digitize and get a digital output. So instead, what people also try is, you take the voltage, give it to something called voltage to time converter. You get two outputs, basically digital signals, whose delay is proportional to the voltage. and then you take a TDC, a time to digital converter, and digitize the time delay between these two. Again, the motivation is because TDCs in principle requires only digital blocks. In principle, I mean some extra things are needed, but you can in principle do it with this. So this is another thing that is being done, but of course it is not straightforward because this voltage to time converter will be highly nonlinear. Because ideally you want, if the voltage is delta V, you want the time to be delta t. If it becomes 2 delta V, you want this to be 2 delta t. This sort of linearity is very difficult to achieve. But of course, people are still trying to work. So let's stop.